Hello everyone, let's get started. In our last video, we discussed integral theorems. In the integral theorems, we discussed three important theorems. The first one is the divergent theorem. The second one is the gradient theorem. The third one is the curl theorem. So these three theorems are very important, which are going to be useful in our continuum mechanics course. Okay, so here let me refresh the cross product, right? The cross product between two vectors, actually curl mean the cross product between del operator and the given vector. The How do we find the cross product? It's actually the determinant of first row you have to list out the base vector, and second row you have to list out the first vector, the vector given first. It is a del operator, so this is the del operator vector component. Then the last row will be the second vector. Second vector is F1, F2, F3. So this will be your curl of the vector. Just a cross product, okay? Just I am reminding, right? So just I refresh what we have discussed in our cross product and dot product lecture series. Okay, so in this video, I'm going to solve two problems uh, using our math preliminary, right? So you can get many uh, exercise if you go through any continuum mechanics books, right? So you can solve very easily. But here I have selected two physics-based problem, right? So one is the normal problem, another one is the physics-based problem, where we are going to apply these things in our physics case, right? Okay, the first one, to familiarize the uh, divergent and curl. So here I have given one position vector here in Cartesian coordinate system. In this case, instead of E1, E2, E3, it is EX, EY, EZ. But again, the same, right? Because this is I have taken from the math book. Now we have to find the divergent and curl. Okay. So first, let me write our given vector in terms of index notation, right? So I'm going to use index notation to solve this problem. You can solve it like our previous way, right? So divergent curl, you can manually do it. But we are going to use, especially I'm going to use index notation a lot for our model. So therefore I use index notation here. Okay, so this is the vector. First I am going to write this vector. This is xi and e, I will write ei, right? Okay, so here I, instead of 1, 2, 3, in this case x, via y, z, right? That's what I have assumed here, right? Okay, this is again I'm going to use the same index notation, right? Then we need the del operator. Del operator, it's a vector. So I will use a different free index here. Do x j e j. Okay, so this is the del operator, right? So here also j again x y z, right? J also x comma y comma z, right? Okay. So now first I try to find the divergent, right? Dot product between the vector and del operator. So del operator, this one, let me write that one here. Xj ej dot product with uh, mm, so this is xi ei, right? Okay. So now again these two, ei and ej and ei, just a constant. It's a unit vector that is nothing to do with the differentiation. Therefore, this one you can take it separately. So now this variable, this vector, I'm going to combine with the differentiation. Therefore, dou xi and dou xj. Okay, so this one ej dot product with EI. Okay, right. So now this one we already discussed, right? Uh, this will be delta Ji. Okay, so I told you always I'm writing the below one first, then the top one, right? So you can write it in other way also because it is a symmetric tensor, right? So Ej dot Ei, again that is the um, chronicle delta, right? Ji. This is something we already discussed, right? Delta I Ji into J, that means delta Ij into Ij. This is we already discussed. It will be delta Ii. That means I am using the chronicle delta property, right? I am removing the J, replace with I, right? Delta II we already discussed in our previous in the math preliminary session. It is 3, right? So therefore we have find the divergent, right? So now let me find the curl. Okay, dot product uh, R. Sorry, now is the cross product, right? Cross product of vector R. First, let me write this one. Do xj ej cross product. Now xi ei. Again, same. These two is unit vector is constant. You can take it out. Combine the variable here. Xi, xj. This will be ej cross ei. Okay. Again, be careful, right? So this will be ej ei, right? Okay. So in the previous case, the I and j, you can write it other way also, no problem, because it is a dot product. But here you cannot change, right? You cannot write ei cross ej, right? Because cross product is different. Okay, so this one again, delta ji. So this will be, you remember, right? We have to include uh, permutation simple, right? J I K E K. Okay, right. So now I'm going to apply the chronicle delta property. What is that? Replace the common index by the another one, right? So I'm going to select in this case J as a it's a common index replaced with I, right? So therefore I K E K. You know this one, right? We discussed the permutation symbols, the property, right? When it is follow this order plus one, right? Opposite order minus one, other order is zero. Because I mean it is other order, not coming ijk, right? So therefore this portion is zero. So that means the curl now zero vector, right? It's true, right? One position vector, it is like a force, right? When you calculate at that point, that means you have the vector here. If you calculate the curl with respect to this point, zero, right? There is no curl here, right? Only divergent will come. So that is what it is, curl free vector, right? It is a curl which we call curl free vector, right? Okay, right. So this is something you studied in your maths. Just I use the index notation to solve this problem. Okay. So now let me take the second problem. It is a physics-based problem, right? Okay. So this is also something you already know, but I am going to prove this one. Why uh, this is uh, satisfied this condition, right? Okay. So what is the question? A uniform, a constant pressure is applied to a surface of a body of arbitrary shape, right? So let's say one arbitrary shape here. Okay, so let me take some arbitrary shape. So in this case, it is uniform pressure is applied. Pressure mean you know, right? It's applied. It's the vector field, I cannot say vector field, it's like it's coming inside, right? It is pressure mean it is coming in towards the object, right? Okay. So this is uniform pressure is applied. I'll take that pressure is P naught, right? Okay. Okay, I'll take P, right? So now prove that resultant moment M on this distributed surface loading is zero. So you have to prove uh, the the resultant moment is zero, right? You know, if the uh, constant pressure is applied surrounding its body, it will be like equilibrium, right? So you can say force is zero. If okay, this is very important point, right? If someone says F is equal zero, he cannot say moment is zero, right? Okay, because this is something you know, this is basic your statics. Because force is zero mean you cannot say moment is zero. Similarly, moment is zero mean you cannot say force is zero, right? Okay, so if equilibrium mean both must be zero, right? Because if it is force is zero, means you know this one, right? There is a couple, it can be coupled, right? Something you studied, right, in your statics. The systems it reduced to a couple, right? If moment is zero, the system can be reduced to a force because that point, the point we are taking the moment, the force can be passed through that point. Okay, so therefore in this case you cannot do this question by saying F equals zero, therefore moment zero. No, it is wrong, right? This is something you know from your statics. Okay, so now what I'm going to do, first I'm going to find the total force acting on this surface, right? Let me take one small element. The area is ds, right? Okay, so now I am trying to find the force acting on this surface, right? The force is the vector. You need one vector quantity, therefore I'll take the unit vector on this surface is n, right? So now you can find the force on this small differential element, right? That is that means force acting on the differential element, right? Or infinitesimal element, right? So that is we'll take df, okay, equal the pressure, right? Okay, pressure is acting actually other direction. I am calculating this way, therefore minus p, okay, into uh, ds is the area. Now it's the value of the force. I have to include normal vector, right? Okay. Why it is negative? Now normal vector is outward direction, the force acting this way, right? So therefore it will be negative, right? Okay. So this is the force on this small different element, right? So now I will calculate. Now what is that? My the point of interest, the point where I am taking the moment, it can be some point, right? With this point, we have uh, one vector, right? So that is our position vector. So this position vector, uh, yeah, this position vector, I'll take as R, right? I use different color, right? Okay, so this is my position vector. It's R. This position vector, in each point, this vector will change, right? So if I consider the 3D coordinate system, my R I can write, okay, like this, right? The point can be, if I take x comma y comma z, I can write this one uh, x ex y ey z ez, right? That means I can write in, if it is an index notation, I can write like this, right? Okay. Right now, so now let's see, I'm trying to calculate the moment due to this one, right? Moment due to this force, right? Df, right? With respect to, okay, any arbitrary point, right? Oh, okay. So therefore now I can find that moment df dm, okay, small moment. This is something you studied, right? In your statics, the moment is the position vector cross multiplication of the force, right? Okay. Right, so this is this one, right? When I write df, when I substitute this one, I can take this minus front, okay? uh, Position vector multiply cross multiplication with this one, right? That means uh, okay, I will p into ds is okay, I'll write it like this, right? I'll write it here, p ds and, right? Okay, so now the PDS is it's a scalar, that is, it will come out minus P uh, ds. So now R cross N, right? Okay, I will write it this one like this. So this is the moment, right? So now this is only the moment due to this element, right? So now I am going to calculate the total moment, right? So total moment, let's say that is M. So I have to integrate, right? So that means integrate over this entire surface, right? Surface integration, right? Surface integration of this one, right? Minus P ds, I will write it like this, right? R vector n vector into ds, right? Okay. So this is the total moment, right? Let me take P is a uniform pressure, right? Therefore P, okay, I can take it out. Minus P surface integration. Okay, this is entire surface, right? So that means my okay, R, okay, I'll write it like this, R cross N ds. Okay, so now you remember something we studied, right? You could remember we studied a curl theorem. Okay, surface integration you can convert as a volume integration using the curl theorem. But remember, the curl theorem, what is that? The normal vector must be front. So now here, in my case, I have a normal vector back, right? So therefore, I can switch these two. If I switch these two, the sign will change because it is a cross product, right? So therefore, I can eliminate now minus sign. I can write it like this, S n cross R ds, right? Now using curl theorem, okay? So now the same M I can write, I can convert this one into volume integral, right? So now volume integral curl, that means del operator into R, right? dv. Okay, so I'm just using the curl theorem, right? This one, right? Okay, so now is the volume integral. This is, this is something, the curl of the position vector, right? This is the one we already discussed our previous case. When you write any position vector, the curl of that vector is zero, right? So this is already we proved in our previous question, right? So therefore, in this case, this is zero, right? from question 1, right? So therefore now moment is 0, right? This is something we have to show here, right? Okay, right. Okay, so this video, let me stop at this point. If you have any problem regarding this question, please let me know. Okay, let me know in the comment section. Uh, I will explain it, right? If you need further explanation. But don't worry, we will do a lot of questions in this my video series. Okay, so again, I am expecting your uh, supports. Please subscribe my channel if you don't subscribe already, and like the video when you watch this one. It's kind of a motivation to me. Also, share among your circle, right? Definitely, it will help you. Again, I am telling you the video I am doing here, so you won't get nice video series uh, regarding the continuum mechanics, right? Definitely you will realize when I start the continuum mechanics part, that means from our my next video, the the kind of explanations I'm giving here, I'm not just self-pricing myself. I'm saying, right, because I struggle a lot when I study this subject, because it is highly math oriented problem. So if you don't understand the math properly, you cannot understand the continuum mechanics, right? Therefore, when somebody explains these things, they definitely ignores many of the explanations. Then they continue from that. But in my case, I'll explain everything as how to get that particular equation, why, everything as much as possible. I explain, right, as much as I can. Okay, so please let me know in the comment section if you have problem. Then see you in next video, right?